Yes, yes. So whenever you get hungry, we stop for lunch. Basically, so to wrap up the rate thing. So the order of magnitude to remember, you see, is per megaparsec cube per mega year. Basically, that's the rate of events. I mean, less than 10 to the minus 6 per year is per megaparsec cube per year, and 1 mega. I mean, actually, the average volume where you get one galaxy is 100 megaparsec cube. But okay, let's not be too picky at this level. And that's why if you're looking for transient of this kind of system, and if you look at random part in the sky, you are 1,000 times more likely to get a supernova than the outcome of a binary merger, no? Because the binary merger comes per million year per galaxy, the supernova happens per century per galaxy. And so if you just look randomly for transient, you always see supernova, you don't see supernova.
So, sorry, basic question. Why do you have two lines in the
because it's the band. I mean, that's the observational band. I mean, we cannot constrain with that few events that we have so far. We cannot constrain to less than that. So the red line limit the observational rate. The blue line were astrophysical prediction from 2010. And by the way, and the green line were the upper bounds from pre-01 LIGO data. You see, so in 2010, there was the last science run. There was not an observation run. They were just a couple of order of magnitude away from detection. Okay, so this is all about rates. I move on. Okay, no, it's not all about. I mean, this is okay. The data are not public for O4A, but you can get this distilled information from the LIGO website about the rate of detection. You see, a definitely changing slope on the rate of detection has been happening at the end of O2. What happened there? Virgo joined in. So despite Virgo having lower sensitivity, despite being misaligned with LIGO, it helps a lot to increase the significance of the detection. Just because one thing is to have a background computing over double coincidence, one thing is to have a background computed over triple coincidence. So even if Virgo contributes with signal to noise ratio 1 or 2, when LIGO contributes to signal to noise ratio 10 or 20, still helps in pull up the significance. That's why you get this change of slope, and this slope basically maintain the same. So here Virgo was not there, but we still have that slope. Okay, that's okay, fine, we do. And so we are now approaching the 230 at 300 detection. So the idea is to go on now until mid 2025. Virgo is horizon for binary neutron star of 50. LIGO's horizon for binary neutron star 150, basically 3 times. And Kagra, no, Kagra is still at infancy, but that's normal. Kagra has just started. I mean, also LIGO took over 10 years to get here. Yeah, but as I said, it's not really earthquakes that matters, no? It's seismic vibration, and seismic vibration happens all the time. The earthquake affected, yeah, it was a 6 months delay. It was a massive earthquake. It was 6 months delay. I mean, if it happened in Italy, the full project would be erased. And you know, massive earthquake, 6 time delay. I mean, and but they are underground. I mean, they are not below sea level, but they are underground, so that helps a little bit. So no, it's not seismic activity that is limiting them now. It's really, you know, to push the interferometer to that level, you need years. I mean, it's just elbow grease.
But there seems to be a change of slope within O4B. Is this related to Kagra or?
No, I think this is really, no, it's not, surely not related to Kagra. Kagra is insignificant for science now, but it will be soon. But
So you mean O5? This
possibly. I mean, if they maintain the expectation, absolutely it will matter. You see, this is the expectation of O5 for Kagra starting in 3 years from now. And LIGO, Virgo, they don't have a firm prediction because, you know, they've been so disappointed that they couldn't join the O4A that they are now reluctant to make prediction for O5. And this is the prediction of LIGO 5. You see a factor of 2 increase in range, which means a factor of 8 in rates of events. So we do really expect to reach the 1,000 of events by the end of O5.
Sorry, this is total events detected or events?
Total events, yeah, the cumulative number of events.
So Why is it constant? It's not improving the experiments?
Not, I mean, it has been improving a little bit, 4A, but it's yes, it's improving, but not. I mean, here the improvement was kind of marginal. I mean, it was already reaching 120 here. Now it's 150, 160. It's not a huge improvement.
Okay, so it's just turning the experiment on and off.
Yes. Also, what matters is also the duty cycle. No? How much time they're actually on. They're usually on 50% of the time in coincidence, because of course, at some point you need to turn it down to pump the vacuum back up, all sorts of things. But okay, so 6 more months of data for 04, then 1 year and a half to get the result published. So by basically end of 26, in 2 years from now, we should have the results, official results of LIGO published for 04B. And then 1 more year and the stars of 05. So you should expect an order of 300 detections to be published by when the data of 04B will be published. And then you should expect over 1,000 of detection in 05.
But there will be an official 04A release or just the whole 04?
If I told you, then I will have to kill you. I don't know. No, I'm joking. I don't know. I think there will be 2 separate releases also because the burden of work is substantial. And so the people who work on that might want to split it. Yes. So 04A, 1 year and a half from 04A will be basically 1 year.
Half of next year.
Yeah, half of next year. Yes, exactly. Yes. There should be within the end of the next year should be a release of 04A. Yes.
And after, at the end of 04, how many neutron star mergers would you expect?
I mean, if there are neutrons, I mean, the data are
2. Okay.
okay. The idea is that if there is this website, GraceDB, you can Google it, where the data are sort of public, but you don't get the masses. You only see the distance, the sky localization, and if it was a neutron, if a neutron star was involved, so that there is a possibility of an electromagnetic counterpart or not. You don't get the masses.
Yes.
So from GraceDB, from this website, you can already guess if there is a neutron star candidate or not. Since there's not a big fuss about it, you know for sure that there wasn't. Otherwise, you would know without the need to go there. Just
But to know how many up to now?
so by the neutron star, we have 2, one with counterpart, one without. And yes, so but here here you get all these candidates that make up this 225, 257 grand total. Okay, and then the future. So this is the 3rd generation experiment you see compared to 2nd generation, which are working right now. Forget A+. A+ is sort of intermediate between the 2nd generation and 3rd generation. And then you get Einstein telescope and Cosmic Explorer going wide in distance. So here in distance, we get to redshift 1-ish. ET and Cosmic Explorer and the peak sensitivity, which would be order of tens of solar masses, can get to redshift 100. So basically, we don't even know if there are binary measures there, because we don't even know if there were stars there in the first place for compound objects that actually emerged. But if we see merger at redshift 20, then we know for sure the population 3 stars gave rise to binaries and gave rise.
I guess that like the rate of detections at that point will be huge. Do you expect to detect only stochastic background and that you can separate, or you can?
Well, we don't know anything. These sources, we don't know if they're there. I mean,
no, like in general, like are you able to discriminate between the different signals because you're going to start receiving like emission of the time, right? Like over the
yeah, I mean, first the redshift helps because the redshift will make the signal longer, so it will be more easy for the signal to overlap and so to make a stochastic background. About the rates, that's completely unknown. I might be 0 or it might form a stochastic background. Basically, nobody knows. So basically what we let me just comment. This is for LISA. For LISA, you have a different frequency band. Basically, you go down with respect to LIGO by 4 order of magnitude. So you go up in mass by 4 order of magnitude. So you see in this peak 4 or 5 order of magnitude, 10 to the 6, 10 to the 7. So since you're sensitive to this total mass, you can even see extreme mass ratio in spiral. So you can have 10 to the 6 and 10 solar masses together, extreme mass ratio in spiral. Again, you get to crazy redshift up to order 20. And so, I mean, for those of like me who do waveform modeling, then this will be extremely challenging because you really need to improve the precision of the waveform modeling so far.
Sorry, what is CBC signal?
Compact binary coalescence signal. Yes, compact binary coalescence is all sort of this merger of compact object. Of course, this merger must be made of compact object, not by extended object, just because otherwise the frequency will be too low. So you need merger, and the object must be compact.
So, when you mentioned the better precision that you need for the Einstein telescope.
No, because I mean, when you see signal to that distance, it means that the signal of 50 solar masses is a much lower distance, then will be very loud. So if you see a signal with signal to noise ratio 1000, which is 100 times louder than what we see now, your waveform modeling must be way better if you want to get all the physics. So
XPM.
it depends on, I wouldn't really go to one specific approximation mechanism, but the point is that at the moment, you want your precision to be comparable to the statistical uncertainty. When you run a Monte Carlo, you have some statistical certainty. It doesn't help if you have a theoretical prediction, which is more accurate than the statistical uncertainty. But the statistical uncertainty will go down with the SNR. So when the SNR goes up, the statistical uncertainty of your Monte Carlo goes down. So you need to improve your waveform prediction. So yes, you take your favorite approximation mechanism, approximation framework to model the binary waveform, and you go to higher order.
So in that line, I don't fully understand that. You mentioned that everything in the detector is very linear, but somehow for having the correct profile fitting, you need to go to like six.
Of course, I mean, to model the source, you do absolutely need non-linearities of gravity.
Propagation of the signal in your detector, not the modeling of the profile that you have from the merging of the sources.
Sorry, we didn't get it.
So you need these post-Newtonian approximations to have the profile correct from the merger of the sources, even though the modeling or when the signal arrives through your detector is completely linear.
So, I mean, the point is that when the signal arrives at the detector is 10 to the minus 20, so forget any non-linearities in the detector. The point is that 10 to the minus 20 is because they 1 over r. And when you go 20 order of magnitude closer to the source, then all sorts of gravity corrections are important. And in particular, all sorts of gravity correction that change the signal to noise ratio by 1 are important. So when your signal to noise ratio is 10, to have a signal to noise ratio change by 1, you need a 10%. But when your signal to noise ratio is 1000, to have a change of signal to noise ratio by 1 is 1000. So you need to model there at the source with the precision of 1000 to be sure you don't lose things here. So yes, at the source, you need all sorts of nonlinearities up to the level of that give you an effect at the signal to noise ratio you are seeing here. And so Alex is talking about precision waveform modeling on Thursday. Thursday. Yeah. Okay. And so, by the way, this is not the end of the story because we don't have to focus on LIGO, LISA, or Einstein Telescope or Cosmic Explorer because there is PTA is already in the business. I mean, it's not for the future; it's already in the business. So PTA is not based on laser interferometry, but it's based on we are here on Earth. We see pulsars. You know, pulsars are very common. We see thousands of pulsars in the galaxy, and basically, order of hundreds of them have been monitored over decades, over years at least. And so in the time of arrival of the pulsar is very, very regular clock, but it undergoes some irregularities. If these irregularities are correlating among different directions, that can only be because of gravitational wave passing by. So gravitational wave passing by imprints a very specific shape in the irregularities of this pulsar, which can be ascribed to a gravitational wave. And it has been published last year, that there is an effect at the frequency of 10 to the minus 8, 10 to the minus 9 Hz. Where does it come, this frequency? Just because of the time of observation. You observe this beam of the pulsar, these are millisecond pulsars, you observe over years. And so basically, irregularities you can monitor over the time scale of years. So in frequency, that's 10 to the minus 8, 10 to the minus 9 Hz. So that's the bound you can get on these irregularities. And you can see, now, not getting into detail, Gabriela, are you talking about this? Okay, yeah. So tomorrow you will know all about this. I don't need to dwell more about that, but basically the irregularities, when they have a specific correlation between different directions, it can only be because of gravitational waves. but it's a completely different frequency range, so completely different source. It might even be not astrophysical source, it might be primordial source, but I mean, you will know more tomorrow. And so this is just a summary. This is the red curve is a third generation detector. The green curve is a second generation detector. The frequency is 10 Hz, 1 kHz. Then if you go to LISA, the sensitivity in LISA is lower, but it's a lower frequency. So in particular, a signal that is happening in merging in LIGO now, then years or tens of years before was in the LISA band because of this shape of the emitted gravitational waveform of the amplitude is f to the minus 7.6. You don't really need to remember 7.6. F to the minus 1 is good enough. So basically, when you go down in frequency, the amplitude of the gravitational wave goes up as inversely proportional to the frequency. But there is a price to pay. The price to pay is the time. The merger here, it takes less than a second. Of course, if you want to accumulate this very high signal, then you need to wait for a long time, just because you're very far from the merger. So the velocity of the binary is much smaller. So it takes a lot of time to emit energy. So you really have to integrate over many cycles. So in particular, this is a standard formula for the time it takes to go to a frequency 1 to a frequency f. Okay, I to f, I to f should be. So basically, you have this typical behavior f to the minus 1/3. I can give you a simple argument why there is a minus 1/3, but I will skip it. Otherwise, people complain that I always talk about order of magnitudes. So, but the idea is simple. Basically, this time must scale as 1 over the mass ratio between the two objects. And this m chirp, oh, I didn't write m chirp. So, maybe next slide. No. So M chip is very important. M chip is defined as M1, M2 divided M squared to the 3/5 divided by mass. So this is dimensionless, and this is the symmetric mass ratio to the 3/5. So it's only this one. So it's the product of the two masses of the binary divided by the total mass is clearly dimensionless, and it's confined between 0 and 1/4. At most, it can be half and half, or it can be 0. It happens that it enters to the power of 3/5 in combination to the mass to form this definition. And basically, this shear mass is the one that sets the dynamics of the radiation reaction of the binary. So the time scale of the radiation reaction of the binary is set by this mass. So it has to go as 1 over the symmetric mass ratio. So since the symmetric mass ratio entered to the 3/5, then this M chip entered to the minus 5/3. And so this is the time. Then you must put in the right power of frequency to give the right dimension. And so the power of frequency is minus 1/3. So what you have to remember is that the time it takes from one frequency to the other is very steep with the frequency. It's basically f to the minus 3. And so if you move down in frequency by 1 order of magnitude, you have to wait 10 to the 3 times more time. That's why basically the signal in LISA will take forever for at least the time scale of the mission to exit the band of LISA, whereas the system in LIGO they sweeps very quickly. Of course, a signal in LISA can also be a transient, but then it has to have the right mass to merge in LISA. Of course, if it merges in LISA, then it will also be very quick, but those will be very, very few. The bulk of the events in LISA will be the ones that take forever, basically, to move around in the frequency band of LISA. Okay, so the thing to remember is just this f to the minus 3, which tells you how long it takes to move from one frequency to the other.
I have a question. You mentioned about this peculiar unit, square root of time, right? It is proportional to the amplitude of the wave signal?
So basically, okay, this is a little bit of the detail. When you compute the signal to noise ratio, this is the formula for the signal to noise ratio square. You take the Fourier transform of the signal, you integrate, so this is square, you integrate and you divide it by the spectral noise density. So the spectral noise density is the one I showed you before, which has dimension of time. This has dimension of inverse of time, and this is dimension of time. So overall, this is dimensionless, fine? So basically, whenever you want to compare a signal, a Fourier transform of a signal to the noise, you basically do this. So you put a f1/2 inside here, you put an f here. So this is an integral and logarithmic of frequency. So this is dimensionless, this is a dimension of time. And now this combination has dimension of time. So basically what people usually compare to the square root. So this is the spectral density, which is quadratic in the noise. So you plot these curves are actually the square root of the spectral noise density. And the signal is actually f to the 1/2 times this, just to compare apples to apples. But okay, these are technical things. Okay, so okay, and this to put in prospect what this pulsar timing array is doing. Pulsar timing array is really up here in very low frequency. And then there is LISA, which will happen in 10 years. And this is the third generation, it will happen in 10 years too. And this is LIGO and Virgo Kagra, which are happening right now. Okay, okay, this is a bit technical. Let me skip to the actual point. So the idea here is the following. Why, basically what I want you to understand in the next 2 minutes is why gravitational waves do not measure redshift, only measure distances. Okay, this is what the message I want to convey to you. And the answer is in this formula. Sorry, it's a bit technical, but that's the least technical I could write. So sorry, this eta is actually what here I call mu. These are the same, just different notation. So this is the amplitude of the gravitational wave. This has nothing to do with the detector. This is the polarization, okay? This is not the projection of the polarization into the detector, so it's nothing to do with those pattern functions I showed you before. So the two polarization, how do they depend on the parameter of the binary? So they are linear in the mass and inversely linear in the distance. Okay, that's easy to remember. So there is a v square here because they're actually not sourced by the mass of the system, but they're sourced by the kinetic energy of the system. Okay, that's also shouldn't be too difficult to swallow. No? So basically, the amplitude of the gravitational wave is kinetic energy of the system divided by the distance. And of course, this is dimensionless because energy is the same as length because g is equal to 1. Okay, there is a factor that depends on the symmetric mass ratio. Of course, if the object is very fat and the other is very small, with a given total mass, the signal goes down, no? Because what is emitting is the guy who is being accelerated. So if the guy is very small, it accelerates very little, so it emits very little. So you're bound to see systems which are more equal masses rather than very unequally masses. But okay, that's also should be easy to swallow. So, and this is something that I just state, I don't demonstrate, is that there is a factor that depends on the inclination of the binary with respect to the line of sight. So basically, if we see something very far, which is perfectly oriented, or we can see something which is very close, which is not perfectly oriented, the two have degenerate amplitude. Okay, just because the emission is preferentially in the plane perpendicular to the plane. I mean, this is something similar to what happens in electromagnetism. No? In electromagnetism, you have zero emission along the dipole. In gravity, you have a reduced emission in the plane of the orbit, and you have maximum emission perpendicularly to the plane of the orbit. So there is a modulation of a factor of 2, basically, of one polarization, and a modulation of 100% actually, depending if you're looking in the plane of the orbit and if you're looking perpendicularly to it. And of course, we cannot know. That's the way it is. We have no access to see what is the plane of the orbit with respect to our line of sight.
So when you speak about the kinetic energy of the system,
Yes.
you know the binary.
Yes. So the kinetic energy of the system is the real source of the gravitational wave, not the total mass.
That is not constant.
Yes, of course. Well, okay, this is a circular orbit. This is in circular orbit, the kinetic energy is proportional to the total energy, and it's not constant because it's emitting. In the circular orbit, the kinetic energy is constant if you forget emission.
In the last stage of the merger.
No, whenever. I mean, so you have kinetic energy, which is sourced in the emission, and then you include the back reaction, and you shrink the orbit, and you increase the kinetic energy because the total energy of the system is negative and is minus the kinetic energy. So the kinetic energy in modulus increase as you go closer. That's why the signal goes up instantaneously, and then you merge, and the signal stops. So you get the kinetic energy is your reservoir of kinetic energy plus potential energy. The potential energy is minus twice the kinetic energy. So the system approaches, the kinetic energy goes up, but the potential energy goes more down by a factor of 2. So the system decreases its energy by increasing the kinetic energy until the object merges and the signal stops. Okay, it's the Wheeler theorem, remember. Kinetic energy goes up, potential energy is minus twice the kinetic energy, goes down. So the potential energy is providing the reservoir for the gravitational wave to go away.
So it's treated as a function of time?
Yeah, of course. This is the amplitude of the polarization is varying. The amplitude of the polarization is varying as your cross emergent is increasing. It's standard. Okay, so what I wanted to see here, I want to say here is that there is this factor that depends on the orientation. So even if we measure the amplitude, and we do actually, by measuring the amplitude, we don't know actually the distance because we need to know what is the mass of the system, what is the distance, and what is this orientation factor. Again, this is not the orientation factor I told you before about the projectional detector. It's the orientation factor of the binary.
For a singular orbit, the system itself will not introduce polarization, but the orientation of the system with respect to us is what is producing the polarization.
No, I mean, whatever source is always producing two polarization. No? I mean, like in electromagnetism. You shake a dipole from electromagnetism, you shake a quadrupole in gravity, you produce the two polarization. What I'm saying is that the two polarization will depend on some intrinsic parameter, like the mass of the object, and will depend on some accidental parameter, which is the relative orientation of the system with respect to us. And this relative orientation of the system to respect to us will enter differently the two polarization. We'll weight one polarization as with one factor and the other polarization with other factor. Now that's normal, no? Because you have two polarizations, basically, these are transverse waves. Whenever you look along the polarization, you shouldn't see the power of that polarization. But these are quadrupolar waves. So the quadrupolar involve two motion. So you can be orthogonal to one motion, but you cannot be orthogonal to two directions. So if you are independent of the orbit, you kill one of the two polarization, but you cannot kill the other. I mean, you always kill one of the two, you cannot kill. If you're looking perpendicularly, you don't kill any of them. And so you see the full. So there is a mild modulation with orientation, but this modulation doesn't kill all of the emission. It can kill a factor of two of the emission.
To distinguish at some point observationally the two polarization, you would have information on how the
Exactly. So with the two LIGO, you measure one combination, the same combination of the two polarization, so you don't disentangle this angle. You need the third detector to disentangle this angle from the distance. But I haven't told you in the first place how to measure the distance, because you see, you still have three parameters. We measure one amplitude, and we measure mass, distance, and angle. I mean, how do we reduce this threefold degeneracy to a twofold degeneracy? Well, through the chirp. The signal is not monochromatic, but is evolving in time. Basically, the evolution in time of the frequency fixes the mass. By fixing the mass, you have an absolute calibration of the amplitude. So the fact that the signal is chirping but is not monochromatic automatically gives a calibration of the system. Of course, you have to assume general relativity. If you change outside general relativity, then the calibration doesn't work in the same way. But the change in the frequency automatically fixes the calibration. And modulo this angle degeneracy that can be fixed by adding more detectors, you have an absolute calibration of the distance. With one caveat. So this is the phase of the signal that depends on time, adimensionalized by the mass, because that's the only dimensional thing you can play with. The phase is dimensionless, so it will depend on time divided by mass. But we don't observe things in the source time, we observe things in the observer time. So when you express things in terms of the observer time, it means that the dimensional factor that you infer from the chirping is not the mass, but is the redshifted mass. And so we multiply and divide here by the redshift. And so basically the chirp allows you to fix the redshifted mass. You plug in the redshifted mass in the amplitude, and so you get an absolute calibration of the distance, modulo this degeneracy with inclination. Okay? So bottom line for non-technical, for people who don't work on this, is gravitational waves are self-calibrating through the chirp, through the change of frequency. Basically, f dot gives a direct measure of the mass, actually of m chirp. That's why it's so important. M chirp is the best measured parameter. The measure of m chirp translates in an absolute calibration of the amplitude that translates in a measure of the distance. Which distance? Luminosity distance. So no information about the redshift, but distance, which is accurately measured. How accurately? Well, it depends on A, the total amplitude of the signal, and B, on this degeneracy with this geometric factor.
But the phase also depends on the redshift.
Well, the phase, we have only access to one phase, the phase of the detector, okay? So you express the phase of the detector in terms of the time of the detector. And that's it. You don't have access to the source time. And by relating the phase of the detector to the time of the detector, you need the mass at the detector, which is not the mass at the source. So for LIGO, this is not a big deal because the redshift are moderate, 0.1, 0.2. So 1 plus Z, I mean, doesn't matter much. But for sure, when you get to redshift 1, that's the whole business. I mean, to nail down the redshift, which we cannot with gravitational waves alone, because gravitational waves alone measure the redshifting mass from which you infer the luminosity distance.
But math that appears in the tables that have been published.
Yes, the mass that are published are the source masses because they've been rescaled by this 1 plus Z. Because as I said, 1 plus Z for the current detection is moderate. So you can assume standard cosmology and say, okay, I measure the distance. From the distance I measure, I infer the redshift through standard cosmology like the CMB value of H naught and so on. And I plug it back to get the source mass. The error I introduced by not knowing exactly the cosmology is usually negligible with respect to the statistical error we measure the masses. So at the moment, it's not a problem, but of course, it's in there. One day, when we get to high precision, we need to fit everything together, the redshift and the masses. But
Sure. And again, how do you get this? Because both H plus and H cross depend the same way on the distance.
on the same way, yeah, but that's the good point. That's a good feature. The bad feature is that they are basically when you measure this is what you measure in the detector is a combination of H plus and H cross. Each of the two has a 1/d dependence. You can scale out, and then there is dependence on this inclination angle. Okay. The point is that these two inclination angles are different for the two polarizations, and you don't know them. So these introduce a source of error in the distance. So by not knowing this inclination angle, because you measure only one combination of the polarization, then you have some uncertainty in the distance. The good thing is that the chirping of the frequency allows you to pinpoint the mass. And the mass is no longer a source of problem here, because usually the mass is the best measured parameter, the chirp mass. So this basically is measured, but not through the amplitude, but through the phasing. This is fixed. What is unfixed is this combination of distance and an inclination angle. But the overall amplitude that hit the detector, you do measure. With some uncertainty, of course, but you do measure. So the overall amplitude fixes the distance modulo this uncertainty of the geometric angle. Okay. So, okay, this is a summary. I mean, this is a nice picture. You know,
Sure. Again, so
Sure.
say again, you know by the GR templates.
Of course, I mean, this is within GR. If you change the deal, then you introduce other sources. And so, for instance, here you would get non-GR parameter that bias the distance.
Isn't there like also like the detector degeneracy of the maps that you show? Because when there's like, depending on the angle that you're having the system oriented towards you, that will give you some, depends on the.
Yes, of course.
And you have the orientation of the.
Of course. I mean, in this factor, there is this inclination, and then there is the pattern function that tells you how the amplitude of the gravitational wave is modulated by the exact position. That's also a factor that enters this uncertainty.
Okay, but they are not completely degenerate because you have two detectors that have two different orientations. So they have.
Well, it depends. The two LIGO are basically the same orientation. So with the two LIGOs alone, you don't break this degeneracy. You really need the third detector with a different orientation to break this degeneracy.
And you said that when we go to higher redshift, then we start to basically mix both things.
Yeah, when you go to higher redshift, then you don't really measure mass. I mean, for LIGO, you can forget that you don't measure intrinsic masses because the 1 plus Z is small, and anyway, you can relate Z to the distance through standard cosmology.
Is there any hope that with ET
No, of course. When you go to AT, then you have to do a full analysis. I mean, what you want to do is to fit cosmology and the mass together. Or you give up and say, okay, I just measured the redshifting masses. I put in my table the redshifting masses, and how to get the intrinsic masses. Well, I really need to do a cosmological analysis. That's why we're here, because we want to do cosmology.
So I have a very stupid question. Masses do not depend on redshift.
Yes.
So this is because you have it's a frequency that you're measuring, and then you're relating to the mass.
Exactly. No, because we are measuring something that changes with time.
Yeah.
So, but it's a phase. So you need, I mean, you need to put in some dimensionful object, which is the mass. And so what we measure is the redshift masses, the redshifted masses. That's what we measure, which is basically the unit of scale of the phase. Because you need a dimensionful scale to measure a phase in time.
Just
In the discussion, I think that there's an abuse of redshift masses.
I think that's the language, but that's okay. People accept it. It's like a parent.
What is the abuse?
Magnet, right?
I was born with the jargon, so for me it's not an abuse.
So that there is some hope to measure H naught if you with ET directly.
Okay. No, I mean, that's why we are here, no? How to use this for measuring cosmological parameters. That's basically starting nowish. Now, in 5 minutes, I will pave the way. I will pave the way how to measure cosmological parameter with third generation, and then of course Raul will go with fully blown cosmology with gravitational waves. But I will. Okay. Now it's important. So what do we see with second generation detector is this curve. This is I mean this is redshift 1, 2, 3, 4, and this is arbitrary units. So we see things up to 0.1, 0.3, and then nothing more. But the blue line is the merger rate that we expect from star formation. Okay, so all these objects come from the collapse of stars. We believe there might be contribution from prime order, from prime population 3 star, but let's assume they start from the collapse of standard star. So the star formation of star we know, we measure it in redshift. And it's not this curve, because this curve is the blue curve is the star formation rate shifted with some stochastic delay. Of course, the stars are formed, they go into binary, they go supernova, and then there's the gravitational interior merger. So there might be a few 100 million years delay. So if you take the Maraude-Dickinson curve for star formation, and if you add a few 100 million years stochastic delay, then you get this blue curve. Of course, this blue curve has a huge uncertainty because we don't know exactly this delay, but this is just representative. And the green curve is given this merger rate, which is the blue curve. The green curve is how much of them will be seen by third generation detector. Basically, most of them. Until redshift 2, most of them. So really, there is a really qualitative change. With the second generation detector, the detector are working right now, we see this tiny bit, the orange curve. With third generation detector, we see most of them. We really see millions events per year, hundreds of thousands per year. Of course, the blue curve is really very blurred. What I brought there is just representative. So we still have 1 or 2 order of magnitude uncertainty, but that's the ballpark. With third generation detector, we'll see most of the events up to redshift 10, if they are there, merger events at redshift 10, they might simply not be there. And this round plot is the same information in a different way. Basically, we are sitting in the center of the sky, and if you look backwards with Cosmic Explorer, that's the amount of neutron stars we see, basically most of them, and the amount of binary black hole we see, basically all of them. Okay, so with third generation detector, we really see most of the merger events. Okay, this is again about the time delay. Okay, so how do we do? Finally, it's noon, and I now that I paved the way, I can sketch how we do cosmology, but then you have Raul who will exhaust all the doubts. How do we do cosmology if we don't have the redshift? Well, we have the distance, but then this was the only case of a bright siren. By bright siren, by definition, is a siren. Why siren? Because the gravitational wave, they emit this gravitational wave, they change in frequency. Gravitational wave, we have the metaphor of sound waves. Of course, gravitational waves are not sound waves, but metaphorically, they are like sound waves. And so they are sirens. And they are bright if they are accompanied by a electromagnetic counterpart. So you see the green little banana is the gravitational wave localization. You see, the light green is the gravitational wave localization only by the two LIGOs. The dark green was the gravitational wave localization by the two LIGO and Virgo. So you see, it was smallish, I mean, few 100 degrees square. And the Fermi, the gamma ray sky localization was much worse. No? So gravitational wave did better than GRBs in sky localized. But then, of course, you go, I mean, all the observatories, they focus there, they tile the sky in different patches, and they saw this transient that wasn't there, say, 20 days before. And so this is an image of the same galaxy with the transit and the image of the same galaxy subtracted by Taurus, which is an observatory in Chile, which has an important Brazilian participation. So one siren event with direct redshift measurement, because the galaxy was identified, and so basically the redshift was measured with zero error. Okay, what do we expect in the future? So this is an expectation for third generation detectors like Cosmic Explorer and Einstein Telescope compared to 04. These are all simulation. So if you look at the blue line, focus on the middle line. So this is the sky localization expectation for 04, for ET alone, and for ET plus 2 Cosmic Explorer. You see, sky localization will never be too big. The bulk of sky localization for 04 will always be at 100 square degrees. So if you look at where is 50%, is of the order of 100 square degrees. If you look at one third generation detector alone, it would be even worse, because you need different detector to sky localize well in the sky to have a good sky localization. Because I told, sorry,
This is for the triangle shape?
this is for the triangle shape. AT triangle shape, Cosmic Explorer L shape. So what is important for sky localization is time delay. So for time delay, you need the separate detectors. So one ET alone will have a poor sky localization. Worse, despite having a better sensitivity, will have a poor sky localization even with respect to current detector. But then if you combine a third generation detector with another third generation detector, then you get to this sky localization. Still, you get few events that are very well localized, but you see the bulk of events, if you look at 50%, there still be tens of square degrees. So the sky localization properties of gravitational wave detector is not ultra great, especially compared to optical. But since this is normalized to 1, since you will have hundreds of thousands or millions of detection, you still have a lot of things to work on. And this is about the distance uncertainties. The distance uncertainties, you see, we get 50%, you get of the order of 20–30% accuracy with the current detection. We get, again, even worse with ET, because again, it's only one detector. So you have this problem in disentangled degeneracy, but then you have several third generation detector. You see that half of the events will have a less than 10% accuracy in distance. Again, not super good accuracy. You shouldn't expect percent accuracy for most of the events, but you will have the bulk of events with less than 10% accuracy. That's the typical distance uncertainty once you have several detection in third generation. And in the sky localization, what you should expect is of the order of tens of square degrees. But again, you need combination of detectors. So why this helps to do cosmology? Because I haven't talked about redshift yet. Shall I move how to pinpoint redshift in these -5 minutes that I have? Okay, the idea is older than me, actually. No, not older than me, no. I'm not the young. But the idea is from 30 years ago by Bernard Schutz. He said, okay, we don't have redshift, but we have sky localization to some extent. And so we look at the sky, we pick all the galaxies that are there, and we pick the redshift of those galaxies. So the idea came in '86, but without much backup from data. And as far as I know, this is the first paper from 2011 that basically implemented Schutz's idea with some specific galaxy catalogs. And Walter Depp also did this. Okay, what is the error in H0 that I get if I take all the galaxies in my sky patch and take all the redshift in my sky patch, assuming that the right galaxy is among the hundreds of galaxies or thousands of galaxies that I see in this sky patch. And the prediction for sort of 04 sensitivity from 50 detection is to get to a few percent accuracy in Hubble scale once I measure several, say 50 dark siren, but with some tens of square degrees sky patch, and they take all the redshift of all the galaxies there.
So make an average of the redshifts, if that's what.
Yeah, basically you look
Without any weights?
You look at
weights?
So here there was the binary, but there were thousands of galaxies.
Yeah.
So basically you get the distance from the binary black hole, you get the redshift of of the galaxies, and you get a PDF with 1,000 peaks. Okay, for this event. You repeat this 50 times for 50 more gravitational wave detection, and you get 50 times this curve. Yes, this is the PDF of H0, which is just the ratio of the distance to the ray for this event. You multiply this by the 50 detections, and what you assume that the spurious peak will cancel, whereas the true peak will blow up. So this was Schultz's idea from '86 that was implemented in this paper. Of course, this was very rudimental because it was 13 years ago, was the first attempt. Now things have been evolving much more sophisticatedly, but this is the basic idea. This is the basic idea of the so-called line of sight method. So you take all the galaxies in your line of sight, you take all the redshift, that will give you a multi-peak PDF for H0. But of course, you might be careful that what if your galaxy is not in your line of sight? Then you get a bias.
I was going to ask something along those lines that is probably more of the discussion, that how is the completeness of the galaxies always?
Yeah, I have a slide on that. Okay, so the refinement of this idea came out in 2019, and the author of this paper said, okay, let's look at the precision of H0 once we have a bright siren. So all the events have an associated redshift. So this is the error in the Hubble scale. Once we accumulate, say, 100 events, then we get to 2% accuracy with 100 bright sirens. What if we add the information of galaxy catalogs of which are 100% complete? So this curve is for dark sirens, so all events without electromagnetic counterparts, but with galaxy catalog complete. So you get a decrease in the error, which is not too bad. And then, of course, you get a higher decrease in error if your galaxy catalog is not complete. Forget about this. So this is in this simulation, this is what they assume about the delta omega, about the sky localization. So the sky localization was supposed to be order of 1,000 square degrees for signal to noise ratio 15, and then to decrease linearly in logarithmic scale, like this. And this is a crucial point. This is the completeness of the galaxy catalog they assume. You see, the galaxy catalog get to critical completeness already below 100 megaparsec, beyond 100 megaparsec. That's why they focus on this analysis to binary neutron star. Binary neutron star, we don't see any way beyond 100 megaparsec. And so they say, once we see 100 neutron star, this is what we get if they all have a counterpart. And this is what we get if none of them have a counterpart, but all of them have a counterpart in the catalog. We don't see the transient, but we see the galaxy in the catalog. But of course, this has to rely on some sort of incompleteness, and the galaxy catalog are not very complete, already very short. So this applies to binary neutron star, but then if you want to apply this to binary black hole that we can see up to gigaparsec, then this problem of the galaxy of the catalog completeness is very bad. But okay, this is the first idea that traces back to Schultz, that of course has undergone a lot of refinement in the 30 years. But this is the line of sight. You take all the galaxies in the line of sight, and you take all the redshift by all the galaxies. And then, of course, there are a lot of caveats. How big is your cone of line of sight? How complete are the galaxy catalogs, and so on.
What's the expectation to have 100 of sirens?
Okay, 100 of sirens, we are already 100 of sirens. The problem is that they are all of them are basically, but one. And most of them, they have worse sky localization than this, because this is a paper of 2018. This was the projection for this. Sorry, I didn't write the number, but this was okay. Yeah, the number of events is written here. This is the projection for this binary neutron star sky localization with 3 detectors. So 2 detectors out of the HLV or 3 detectors. So this is a projection for say 100 of events. I think the total number of events was 256. Yeah, here 256 was the number of events they simulated. And so they got out of the simulation this scatter in the sky localization. This is for the expectation for double coincidence for 2 detectors, and this is for triple coincidence. And for 257 events of binary neutron star, so that you can see up to 100, 150 megaparsec, this is the precision you get if you have counterpart. This is the precision you get if you don't get counterpart, but you have a complete galaxy catalog, and so you lose if your galaxy catalog is not has that degree of completeness. So that's the expectation by the refinement of Schutz idea. Yes. So you get a Hubble scale of the order of 1%. This is 10% with all the order of 100 events if they have this scale localization. The problem is that we do have 100 published events now, but for most of them, the scale localization is really crappy. Only for 10 of them, the scale localization is below 30 degrees squared. And actually, Clesio, we will talk tomorrow about the basically latest effort to use the well-localized events, published events, to measure H0. Okay, this is some other inference that you can make with gravitational waves. So this plot is about the mass. So this is something intriguing that is alluding to something I will talk about in discussion session if there is extra time. So this is the distribution of masses, of intrinsic masses. Of course, most of the masses we see are 40, 50 solar masses because we can see them farther away. So that's where we see them. But the lower masses must be dominating the population. And the funny thing is that there seems to be not a simple power law. A simple power law for the primary mass doesn't fit the data. So apparently there is an excess of events at 35-ish solar masses. That's why people say in literature, they refer to the spectrum as a power law plus peak. So there is a simple power law. This is logarithmic scale, so the slope you can fit with the power law to -2-ish. But there is a peak of 30, 35 solar masses. This is strange, but at the same time, we don't have lots of statistics. So before making strong statement about what gave rise to this peak, I would be careful and accumulate more statistics. Otherwise, there are a lot of people that got excited with primordial black holes, which of course you can do, study primordial black holes, but at the moment I would say that this is not such a strong hint of exotic physics. I mean, it's not ruled out, of course, but 35-ish, 35 solar masses. I have a slide later in which I give a tantalizing suggestion where these 35 solar masses may come from, but it's very speculative, so I don't want it to be part of this discussion. This discussion about solid data, and then we can have a discussion about speculations. Okay, so I mean, this is the power law plus peak you hear in literature. Basically, this is the mass, not of the detected mass, but the underlying population that should give rise to those population we see. So a lot of stuff at 10 solar masses, as it should be. In our galaxy, we see black holes at 10 solar masses, 15 solar masses. That's totally fine. Then goes down with the power law, totally fine. The peak at 35 is sort of awkward. It's something to speculate about, but we need more statistics. Okay, and then the rate. Okay, these are the same, just focus on the right plot. The rate, it follows the star formation rate. So the dashed line is the star formation rate measured in redshift. Again, we don't know the redshift of the events, we know the distance, but at this level, we can convert redshift to distance with the standard cosmological scenario at this precision. Doesn't make any difference. And so we see that the rate we measure, of course, when you start splitting events into redshift bins, you start losing statistics, so you get the wide errors. But at the moment, there's no serious separation of the rate of merger from the rate of star formation rate. You may say, well, the star formation must happen before the merger, you must have delay. Yeah, but apparently this delay doesn't change a lot the shape of the merger in this range of redshift.
In this game of these spectral sirens and these features, from the star formation theorists, is there any understanding of whether this peak, because it's kind of conditioned on our understanding of nearby stellar populations and synthesis, does this hold? Does this peak even exist as you go to higher redshift?
Okay, the spectral sirens is something, the one Nick is alluding to, is something different than the peak at 35 I'm telling you about.
So
people talk about spectral sirens in this context. They say, you remember 1 hour and a half ago, I told you, I told you about mass gaps. Okay, there is a mass gap between 2 and 5, the low mass gap, and there is a mass gap at 60 solar masses. Okay, so that's an intrinsic mass gap. That's because of the formation mechanism of the system. Okay, this is the comes from the collapse of stars.
But the peak is also information, right?
Sure. The problem is that peak at 35, the weird peak at 35, we don't know where it comes from.
Oh, but even the peak of the very low masses, I've also heard people use that as a
No, but I mean, let me separate the two things. I mean, don't get confused, at least in my understanding. So there is this peak at 35 solar masses that we see, and we don't know where it comes from. It's just a fact that there is an excess with respect to a simple power law. This is the black hole mass function of the primary. The primary is by definition the one in the binary that has higher mass. Okay, the one in the binary that has higher mass. What I mean, if you don't know anything, what you do, the uninformative prior, you put a logarithm. Okay, and you put a logarithm with some, so you put a power law, and the power law doesn't fit. You need the power law plus a peak. Where this peak comes from, nobody knows. This is a puzzle. People claim, there is a contribution from primordial black hole. I mean, it can be, but at this moment. Now, there are people who are trying to do something different. They say, since we measure the redshift masses, if we know by solid physics that the spectrum of black holes must have a feature because binary neutron star cannot be more massive than 2.5, because we know the nuclear state, the equation state of nuclear matter, then we can use that, the physics of the mass gap of neutron star between neutron star and black hole, to fix the redshift in a statistical way. Okay, because this is the primary mass of black holes. But I mean, you can make this plot for the distribution of masses of neutron star. Of course, at the moment we don't have enough statistics, but you can play this game for ET, where we expect to measure hundreds of neutron stars, and we look at the distribution of masses of neutron star. Since we know that by nuclear equation state they cannot go beyond 2.5, whatever we see beyond 2.5 must be ascribable to the redshift. And so we use that feature of the spectrum to fix the redshift in a statistical way. And if you do that, you can measure in the plane of Hubble scale to omega matter. You have these curves. What is gamma? Gamma is the parameter they use to blur this bound because of cosmological evolution. I mean, things may change between now and redshift 1, so you might blur this feature by this gamma factor. And you say, even by blurring, by blurring this feature with this gamma factor, you can get this precision of 10%, 85%, by using the feature that the fact that compact objects should not exist beyond the neutron star limit. Okay, this is the spectral Siren matrix. You shouldn't have in the distribution any feature beyond the neutron star limit. Of course, with LIGO, it's very difficult to do that because we have two binary neutron stars, but with ET, we should be able to do that. And then there is the second feature, which is the high mass gap. The high mass gap due to the pair instability of the electron-positron creation. The problem is that we already see an event in the pair instability gap. So we don't know how solid is that gap, because that gap relies not on nuclear physics, but relies on astrophysics of the system. So you see, but of course, provided you state your assumption, you can do whatever you want, provided you are safe. This paper states the assumption.
But this figure is the implication then that if you have a minimum, if there's definitely evolution in the location of this edge, because it's the gamma min equals 0.1, then you're biased in what you measure for omega matter.
Exactly. The idea is that if you try to do the fit with and without allowing an evolution of this feature in the
they're not
spectrum,
allowing it in their model.
so it depends. No, gamma equal to 0 means so this is the range of gamma. Gamma, the blue is gamma to 0 to gamma to 0, so no evolution, and you get this this thing. If you allow some evolution, you get the green. And if you the red seems always equal to the green, but a very different result.
The red is there definitely is evolution in the model.
Exactly. And the green is there might be no evolution in the model. So so if you definitely have evolution or not, you can easily bias your result. Right. So bottom line, I mean, without getting into much details, I don't think you should overtrust these results.
Somewhere that you should have a, you have a redshift measurement, right? And you know how it propagates. All the features should go as 1 plus z, right, in the spectrum, right? So even if you have evolution, unless it's exactly like 1 plus z, then you can disentangle. If you have evolution which is exactly like 1 plus z, then it can be degenerate. I think that's the
the bottom. I mean, the take-home message for non-expert in this specific topic like me is the following: if you have known features in the spectrum of the mass, what you can do is you infer the redshift population-wise by fitting the known feature. The problem is that then your result relies on the known feature. So for instance, the mass gap for binary neutron star, it should be there, but again, it has been put into doubt by the recent events I mentioned earlier. There was a 4.5 to 2.5 binary system that has been detected. It's a neutron star that violates the equation of state of nuclear matter. It's a system that wasn't formed by collapse of a star. I mean, we need more statistics. But if you trust the feature that there should be a gap between neutron star and black holes, you can use this to fix in a statistical way the redshift. And so you can get 5–10% accuracy in the Hubble scale. But then you have to have a caveat if you allow or not for the variation of this exact position of the mass gap with redshift. So there are caveats. So this is the spectral siren method. It has, as far as I see, nothing to do with the peak at 35 solar masses, because that's really, it's not based on any physics we know. It's there as a fact, but we don't know where it comes from. Whereas the mass gap between 2.5 and 5, we claim we know where it comes from. It might not be there at the end, but we think we know where it comes from. It comes from the fact that neutron star cannot be too massive, and black holes must be more massive than some amount, just because otherwise the astrophysical collapse doesn't have enough mass to prevent the re-explosion.
Sorry, but in order to use this method, we have to be sure that it is a neutron star. Neutron star.
Exactly. Yes.
And, but then to infer this, you shouldn't infer this not only with the mass, you should infer this with.
And you should see some tidal deformation, of course, yes.
Yeah.
So this applied to the existence of a mass gap between neutron star and black hole once and for recognized by the neutron star. You can play this game also with the higher mass gap, but then higher mass gap is even more shaking because we don't really know, I mean, much about the higher mass gap. This mass gap is 60 solar masses because stars too massive, they would just explode instead of forming black holes. So this is the spectral siren method. Use known features in the intrinsic distribution of masses. And then there is this last method, which is statistical correlation, but since Raul will talk extensively about it, and we are, yeah, I think I can stop here. And then this slide, you see, the title is speculations. So it's not for this talk, but I prepared something about primordial black holes in the speculation session, because, and so I can stop here, but I skipped, a huge chunk of cosmological inference that will be covered by Raul.
We have plenty of discussions, and we have more discussions after Raul's talk. But if there's any urgent question. Okay, so we come back at 2 o'clock. Let's thank Riccardo again.